So it's quite a creative machine, isn't it, really, when you think about it, these things. And so the linkage, of course, is that all of these rely on flow in pipes, right? And so it's the kind of questions that we might want to answer. Certainly we've worked with conservation of momentum, and so we know how we could calculate exactly what kind of force comes out of one of these jets to be able to lift a human, a body, and the weight of the fluid in the umbilical that has to come up as well. So we could do that calculation. So we should be able to work out exactly what flow velocity we need to come out of the nozzle to do that. And so the topic of weeks 10 and 11 really would be what kind of losses do we expect to get in the pipe, and trying to dimension the power that you need from this sled, I guess, that trails on the end of the umbilical, which clearly has a pump in it that supplies the power to this system to be able to lift these people out of the water on top of these jets. And so that's maybe an interesting application of kind of, I think, a bit of a mundane topic, which is this pipe flow stuff that we're dealing with now. And of course, it revolves around this idea that we broached last time, the last couple of sessions, and that is the flow of fluid within a pipe. We can calculate the losses that occur. Clearly the energy we put in upstream is not the same energy that we yield downstream, because there's work done against the side of the pipe. And the magnitude of that work we think we know how to calculate, and we know that it scales in some way with the fluid state. And so as the fluid velocity is increased, Reynolds number increases proportional to fluid velocity, then the losses on the walls of the pipe, which occur to make the pressure at the downstream end different from the pressure driving it at the upstream end, we can calculate those. And so we can account for what kind of pump head we might need to be able to drive flow downstream. So that's essentially what we're attempting to do now. So if I pause that and we go back to where we were before, and talk about what we might talk about today, that's kind of where we are. So let me get us back here. And so so far, I don't know if I'll jump between screens. Yeah, I guess maybe. We spent some time doing this. We tried to make the case that pipe flow is actually no different from the other kinds of flows that we'll look at in weeks 12 and 13, external flows and open channel flows. They all revolve around this idea that we have losses within a system, and the easiest way to unify these is that the expression that we broach that we would end up using, which is the Moody chart, looks something like this for pipe flow. It's a function of Reynolds number against the frictional loss. And we said exactly what that would look like in summary. In the laminar regime, which, if I do something, it's not very convenient to. So in the laminar regime, and laminar here, this number here is something like 2000, Reynolds number of 2000. We get a very specific kind of flow. And in the turbulent regime, then the lines look something like this. And we'll see this many, many times. These lines are each for a different roughness, which we call epsilon d. And so this is for a big roughness. This is for a tiny roughness at the bottom. But they allow us to be able to characterize exactly what the friction factor is that we want to use. And we said last time that this friction factor contributes to the head loss in the system by an expression which scales with some geometry of the pipe and also the inertial part of Bernoulli. And the only reason for maybe doing this now is that in the weeks to come, when we look at external flows, we'll find that the drag that gets applied to an object as air flows or fluid flows around it is defined in terms of a coefficient of drag. And actually a coefficient of drag is exactly the same as an Euler number. And we'll find that it looks something like this. I'm just doing it simplistically as a function of Reynolds number. And so this is coefficient of drag. It's also Euler number. It's the same idea as before in that this stuff here is turbulent. And to the other side, it's laminar. And so you see a striking similarity in these figures. This is the drag which is on the exterior of a body, a water tank or something, or the nose of a plane. And it changes in characteristics from laminar behavior where it's dominated by viscous forces to turbulent behavior where it's dominated by the mixing of the fluid. But it looks identical to the behavior for the internal drag. And when we look at, there is no such equivalent diagram for open channel flow, but what we would find is that if we defined a Manning number, which is again also similar to an Euler number, as a function of Reynolds number, we'd end up with a whole bunch of lines, again, that look like this for different kinds of channels. And so for channels, these would also be relative to their roughness. So one might be a glass channel, one might be a concrete channel, one might be an earth channel with different roughnesses attached to them. There would be a laminar part in this regime, but we don't care about this because almost all flows in open channels, because the Reynolds number is big, are almost all turbulent. Oops, I don't know why that happened. I don't really want to see my email. It's boring. And so there's some commonality between all of these. So that's kind of a longer than I expected preamble, but a preamble nonetheless. So that's where we're going. So we introduced Moody Charts last time. So if we go back to talking about what we might do today, then maybe I'm going to make this larger so I can use the whole screen. I realize that you're going to miss some of it. I know exactly where that goes now. And so, our basic idea is just to maybe recap what we talked about in terms of Bernoulli equation. I'll use my favorite color again. And so, for instance, I guess you could imagine that this would be something like the guy or gals on the jet machines, whatever they are. We know that, that they sit here, and if we wanted to write the relationship that defines, for instance, the flow rates that come out of the system, then I suppose we would number these nodes 1, 2, 3, 4, 5, etc. And we'd write an energy equation, which is the one that we want, which is merely the same form as we've had before. Elevation plus pressure plus velocity head plus pump head has to be equal to the same components, in this case 5, I suppose, in this case, if we write it between those two. Plus 2 sets of head loss equations. Head loss, hopefully you can still see, head loss major. And are we off the screen now, or almost? Head loss minor. And those are different just depending on the conditions. So the major ones are the ones in the pipe, and the head loss in the pipe is going to be equal to the friction factor of the pipe, its length to diameter ratio, and the velocity in the pipe. This is the velocity in that particular pipe, wherever it might be. And it's the sum of all of those to get to that point. And the other one would be the minor losses. And we also defined those. We didn't look very closely at them, but those are usually equal to some coefficient multiplied by the velocity inside that fitting. So these are the local velocities that would be in those individual components. And so in this particular case, these head loss terms, I suppose, would be written out, and they'd be the sum of the head loss terms for the major ones would be equal to the head loss 1 to 2, so something in this pipe here, etc., plus the head loss 2 to 3, etc., all added together. The minor head losses would be the individual ones. There'd be an input head loss, which we'll talk about in a little while, and that would be something strange there. Head loss in fitting 1 plus head loss in fitting 2, etc., all the way through to head loss 5. And this would be through to head loss 4 to 5, etc. And each of these can be recovered just from noting the individual components. And so in that way we can start putting things together to be able to figure out exactly what the one unknown would be. And I suppose the one unknown that we'd want in this particular case, maybe we prescribe this. And I suppose also, I guess we didn't identify this, but the pump head is always equal to what? The power in the pump in watts divided by G times the mass flow rate, which is the same as the power divided by rho G times Q. Flow rate and power. So power is the rate of doing work. So joules per second is watts. And so in this, I suppose the pump would be sitting here, and that would be added into this equation on the left-hand side. So you have enough to be able to do this. So for instance, in this particular case, we'd be able to define all these components. We'd know exactly what the velocity we'd want coming out of the system at the end would be, and therefore, if, for instance, the pipe diameters were all the same through here, the velocities by continuity would be the same throughout this sitting, and we'd know what those velocities would be to be able to calculate the head losses. And basically, I think what would come out of this, if you ignore the difference in the slight elevations, well, I guess what would come out of this would be well, no. For these particular cases, the pressure where it goes in is going to be 0. The pressure where it comes out is going to be 0. If the flow rate into here and the flow rate out of here are the same, then this term and this term will cancel. And actually the expression that we'd be left with would be that Z1 minus Z2 is equal plus the pump head is equal to the sum of the major losses and the sum of the minor losses. And both of these terms here are a function of v squared over 2g and some other terms. But so long as we know what the velocity is that we need to do this, then we would calculate what the pump head would be. So that's basically what we might want to do. We've said something about the Moody chart last time. I'm sure we'll say more about it today. But what we might talk about are what the magnitudes of these minor losses are. It's relatively straightforward. Really, this figure absolutely encapsulates what those are. They never change from that. And it really says something about it which is relevant to, which relates to the Moody chart. And I suppose that feature is that if we look at the Moody chart, the features that we know is that in the laminar regime, on this left-hand side, the friction factor, or the drag, so this would be the head loss is equal to the product of friction factor, some characteristics of the piping system, and how quickly the fluid is moving in it. So this friction factor is a function of Reynolds number. So as Reynolds number increases, the friction factor goes down because they're inversely proportional to it. And so in this regime, the friction factor is proportional to Reynolds number but independent of roughness. We made that point last time. In the turbulent regime, in other words, to the right of 2000, Reynolds number of 2000, so this is turbulent, and this is laminar. Then, importantly, in this regime, all of these terms happen to be independent of Reynolds number, right? You get the same value of friction factor irrespective of the Reynolds number as you move in this above some threshold. And so the fact that they're horizontal means that they're independent of Reynolds number, but they are strongly a function of roughness. So really rough pipes and really smooth pipes have different magnitudes of these friction factors, and it changes the way in which we solve the system of equations. So the fact that we tend to represent the minor losses by a coefficient, K sub L usually, is merely suggesting the fact that always in pipes the flow is assumed to be turbulent, because it's equivalent to being in this region on the right side here, where it doesn't change with Reynolds number at all. It varies only with the physical characteristics of the pipe. Those happen to be the roughness of a pipe, or for individual fittings, it would be the geometry of the pipe. So I suggest that today we look briefly at minor losses to see what they are and how they vary. It's not very exciting, I don't think, probably quite necessary. For instance, if we want to do this calculation, we need to know exactly what those are. And also entry and exit losses, where fluid comes into here and goes out of here. They're also classified in the same way through these loss coefficients. And then maybe, depending on time, we'll do an example to be able to look at pipe flow. So that's probably the best thing to do. Yeah, okay. Actually, so the other thing that we can make the point of is that when we look at major losses, the fact that the head loss is equal to the friction factor, length over diameter, and v squared over 2g. If we look at the equivalency in terms of minor losses, such as the loss coefficient times v squared over 2g, then this loss coefficient is really the same as the friction factor. We've already said that this is really just the same as the Euler number. And if you rearrange this term around in terms of the controlling factors, you see that that's exactly the case, right? We know the Euler number as a pressure divided by rho v squared. It has some extra coefficients in it, but that's basically what it is. And so that's useful to be able to deal with that. We've made the point already that it's a function of the fitting. You can define it if you wanted to as an equivalent length of pipe, just by playing some games, by realizing that this has to be basically a loss coefficient, and if you rearrange it in terms of KL, then you just get this. So that's one way of looking at it. But the physical characteristics of this are that it varies with the geometry of changing flow. We made the point last time that as you go from a stagnant tank that has no velocity to moving in a pipe, physically you're accelerating something. Zero velocity here, some velocity here. And so the fact that you do that means that you have to, from F equals ma, if you're accelerating something, you have to apply a force to move this packet of fluid here to this point here. So you have to apply some force to it. And so that force that you're applying to accelerate it from zero velocity to some finite velocity is eaten up as energy delivered to the system. And so as you can imagine, the loss coefficients for different entrance conditions vary depending on the severity of the acceleration, how quickly that acceleration occurs, or over how short a length, I guess. So you think of how quickly an acceleration occurs to you as you go in a car, but you can also think about how quickly that occurs in space as that car travels. And so when the disruption is biggest with these flanges on the outside, then it's a big number. As you progressively smooth it off to make the acceleration more gentle, then those losses become smaller and smaller and approach zero at some stage. You could imagine also that when you change the radius of curvature, which is really what this is doing here, right? If you change the radius of curvature to make this a more gentle acceleration, then you make the loss coefficient progressively smaller and smaller. So as you change the radius of curvature relative to the diameter of the pipe, then from a very small radius of curvature, so I guess this would physically look like this, right? This point here. Zero radius of curvature would be a very tight corner. And you'd imagine that would have the largest loss coefficient, and as you make it progressively smaller and smaller, or smoother and smoother, it goes to be smaller. Exit losses are the same thing. You're decelerating a fluid, it's going at some velocity here. In a stagnant tank, it's going at zero velocity some distance away from there. And so again, the geometry of the exit seems to matter less for some reason. I don't know why. Even with a relatively gentle change from a prescribed velocity to zero velocity, these magnitudes don't change very much. I'm not really sure why that is. And you can look at the form of even changes within the cross-sectional area of a pipe as it goes from a wide pipe to a narrow pipe, then how the magnitudes of those loss coefficients should change. Large when there's a big difference between them. When the relative areas are the same, in other words, that means that the area downstream is exactly the same as the area upstream. Not surprisingly, the loss coefficient, you'd imagine it should be this value. And as you get to, well, this value here should be zero, not this. And as you get a bigger disruption, you have a loss coefficient which approaches half rather. The same when you go exit from the relative areas. If you change the areas to be 1 again, so there's no change in the cross-sectional area of the pipe as you go downstream, then you'd expect there to be zero loss, and of course that's the case here. And as you have a bigger change as you go into an infinitely large tank, it approaches 1, as we saw in the previous cases. If you change the angle at which it goes into the tank by making it more diffuse, so I guess 0 angle would be a pipe that doesn't change diameter. This would be basically 0, and you see, well, I'm not sure why this is going up. I guess it doesn't go to 0 exactly. But as you have a small angle in here, you have a small loss coefficient. As you have a large angle in here, I guess 180 degrees is this. This point here, where it becomes 1, as in going into a big tank. And so those are entry and exit conditions. And other behaviors in fittings, which are defined in terms, again, of the shape of the fitting, even going around a bend in a system. And so there are many tables that give you values for what those should be. They should all make sense. They're all defined in terms of a single loss coefficient. They're constant, which requires that we're assuming that the flow is turbulent. And they vary depending on whether they're flanged. In other words, a flange would be like copper piping in a house, or PVC piping, where there's just two pipes joined with a larger diameter pipe on top of it as a flange, which would, for instance, connect the other tube here, relative to this flange, for instance. And so for a flange, you'd expect that it's the smoothest transition into the fitting, and the fact that it's going around a 90-degree bend gives you some loss. That loss is larger for a threaded fitting than it is for a flange fitting, just because of the roughness that you'd expect to see at the inlet and outlet of that bend. If you increase the radius by making it more gentle, then you reduce the amount of the loss from each of these two conditions. If you only go around 45 degrees and then exit from this, then you have less of a loss, not surprisingly, than if you go full 90 degrees for each of these conditions. So these two are less than each other. I guess they're otherwise equivalent. 180 degree bend. Kind of interesting, actually, that this is less than this. Not sure why that would be, but these have been measured. And also in going through other fittings. For instance, even if you go past, even if there's no flow in this direction, because maybe this is capped off, or maybe there's a faucet on here which is closed, there's a loss that you go across this boundary, which you can imagine, and it changes depending on the forms of the fitting. And if you actually have this capped off here so that the flow is around this bend, then you can calculate exactly what those would be as well. If you have a connection, as we said before, as a union, valves, these are big numbers, so most of these numbers are between 0 and 1, as you see. Some are slightly larger than that. Going through valves and gates are much larger. I'm not sure what a swing check is, but anyway. And because you're going through a tortuous flow path. So these are kind of global fittings on pipes. The flow in is through here, the flow out is through here, but to get to that, it has to get through this opening here, which is raised by the action of screwing this connector up to allow flow to occur. And so if you go through this when it's open, it's quite a tortuous flow path, and therefore you get large energy losses within it. And so that's the mechanism by which we can get the numbers that we alluded to before that we want to be able to put into this expression here. So these are now just going to be individual components, which are loss coefficients multiplied by the appropriate velocity, again to be remembered, that is in the actual fitting itself, fitting or the pipe or the bend, etc. So we need to be able to do that. So that's it. So we should be able to do this if we so wanted to. So that's fine. So what we might do is mess around with some examples of that. And I think I can think of an example to do. Yeah, all right. So by way of an example, we could think about using the Moody chart to go, not worry about fittings for now, but merely to go back and to and do the calculations for this. So what we'll talk about in the near future is that, I guess we could talk about now, is types of flow problems. And types is used very specifically here to represent kind of a classification of different flow problems, all in pipes and fittings as individual flow systems. And I'm going to draw a chart which talks about the geometry. Has 4 columns in it. Geometry, flow rate, and pressure drop. And for each of these, we can define the variables that define that. So geometry would be the length of the pipe, the diameter of the pipe, and its roughness, I suppose. Flow rate would be volumetric flow rate or velocity. And pressure drop would be delta P or the head loss, I guess, would be the 2 parameters that go in there. And so what we can do is we can define 3 different types of flow solutions, if you like. Not type 1, imaginatively referred to as type 1, 2, you can probably guess, 3. And all that they suggest is that for each of them, we want to be able to determine one set of parameters. It's not going to. No. Where the other components are defined. And so these look somewhat symmetric. So in other words, these different flow problems are or evaluate, I guess, where these other parameters are prescribed. So these dash parameters are prescribed, and you want to define what the unknowns are in the system. And I suppose in that order, they are in order of increasing difficulty. And really the difficulty arises is that in any case where we have velocity prescribed, then immediately we have the Reynolds number also prescribed, right? Reynolds number is a function of velocity, a characteristic dimension, usually the diameter of our pipe, and the density of the fluid that's flowing, divided through by the viscosity of that fluid. So ratio of inertial, v squared over 2g forces to viscous forces. So this is noted by this. And so if we know the velocity already for this, we know exactly where we are on this particular spectrum here. So if we know where we are, we immediately know when we go up here, if we've got a rough pipe or otherwise, we immediately know definitively what the friction factor is. We don't have to iterate for it. However, in the cases where velocity is not known and needs to be determined, then we don't necessarily know where we are on this spectrum. And so we have to make an initial guess as to what the velocity might be, calculate a Reynolds number, calculate from that Reynolds number the appropriate friction factor, and then do the calculation with that friction factor to be able to see if the velocity that we've chosen is consistent with the friction factor that we've already selected. So we go through an iterative process. So that's the challenge in this, in terms of these different types of solutions. And so it might be worthwhile just wetting our teeth, cutting our teeth, wetting our whistle, I suppose, and other euphemisms, by solving a type 1 problem. And so what we can do is we can calculate for, well, we can give ourselves a geometry. And for that geometry, there'll be a flow velocity, there'll be a pipe diameter, there will be a viscosity and a density of the fluid. We'll choose water. I suppose we could have a relative roughness, which we could define. And I guess the other parameter that we need, other parameters we need to define are a length of the pipe and pressure drop. Delta P. And so, the easiest way to do this, I suppose, is to have this pipe where this elevation Z1 and this elevation Z2 are the same. And so if you write the energy equation for this system, it's this. No pumps, but Z2 is equal to the head loss, plus the head loss. And that's just going to be friction factor, length over diameter, and velocity squared over 2g. It's going to be the average velocity, which this always is, right, as we talked about last time. And so if the elevations of the ends of the pipe are the same, then these terms end up being equivalent to each other and drop out. If the velocities, if the cross-sectional areas at both ends of the pipe are the same, then we also benefit from the fact that these two, they're not zero, but they drop out. And we'd be left that delta P1 minus P2 over unit weight is equal to friction factor, length over diameter, V squared over 2g. And that's just by definition exactly the same as head loss in our system. In other words, upstream pressure is larger than the downstream pressure. That loss in pressure is basically dissipated by the force that's applied to the pipe by the flowing water. So you physically have to hold the pipe against that drag, internal drag of the fluid. And so we can calculate what the head loss. So we said that this type 2 problem that we want, type 1 problem that we want to evaluate, we want to figure out what this is, but we need to know what these other components are. And so we need to just choose a geometry that fits that. And so let's do that. So first of all, we have to calculate Reynolds number. And Reynolds number is going to be equal to velocity times diameter times viscosity divided by viscosity. And so the problem is that if we want to be able to do that, we need to know what the velocity is in the first place that we need. So we have to kind of choose that. So since we want to maybe do this for both laminar and turbulent, let's calculate what Reynolds number is as a function of velocity. So keep velocity outside. Diameter, let's use 10 to the minus 2 meters. That's a centimeter. So this, no. a little less than half an inch. Density of water, (10⁻³ kilograms per cubic meter, and the viscosity of water is of the order of 10⁻³ Pascal seconds. A good number to know. And so the Reynolds number is going to be equal to the velocity multiplied by, this is 10⁻⁶, right? 10⁻³ divided by 10⁻³ is 10⁻⁶. 10⁻² is 10⁻⁴. It's not dimensionless. This has to be in units of meters per second to give us the right number, but we can do that. We said that we want to choose some numbers which are both sides of the laminar turbulent transition. 2000 is right here. So we'd like a number to represent laminar behavior should be less than 2000. So if we want it to be laminar, then certainly if we choose a velocity equal to a tenth, right, that would give us 1,000. So v is equal to 10⁻⁻1 meters a second. Gives us Reynolds number equal to 10⁻⁵, which indeed is laminar. And I suppose if we wanted to be turbulent, we could give, well, we'll do that later. And so if we do that, we know that the Reynolds number is equal to 10⁻³ for this particular case. And so what we can do is we can go from 10⁻⁵, which is right here, up to this point. Are we still on the screen? I think it's, no, actually it's quite close to that. So 0.07 is the friction factor. So, in other words, friction factor is equal to 0.07. And so from this expression now, we could calculate the head loss as being a function of that, I guess. So in other words, the head loss is equal to the friction factor, which we know the length over diameter, we know velocity squared over 2g, so we've chosen that. And I suppose in these terms, do we know everything we need? I think we do, right? So we know the velocity, we know this, we know the length of a pipe, I didn't say, but I'm going to choose a meter long. It's our choice. We know the diameter, and so this would be equal to 1. This would be equal to 10⁻². This is equal to 0.07. Yeah, I hear someone whispering it. Thank you. And we got it. So we know what the head loss is in this system. And it should close because we've already calculated the Reynolds number. So we can do it merely by solving it. We're prescribing a velocity, we know it's laminar, and therefore we can calculate it directly without iteration. If we look in the turbulent regime, we do the same thing. Again, we need to choose a velocity so that the Reynolds number is greater than 2000. So I suppose if we increase the velocity by a factor of 10, instead of being, so v1 times 10 is equal to 1 meter a second. And we know if we put that into this, then we'd end up with Reynolds number is equal to 10,000. And if we go here, well, let's okay. For obvious reasons, let's use a number that's bigger. Let's increase it by 10⁻³. So that would be 100 meters a second. And this then would be 10⁻⁶. Just makes it easy. I won't write that. It'd be 1,000,000, of course. Hopefully 10⁻⁶ is on here. And then if we choose, we'll be done soon, a value of some roughness, then we just have to go up again. So this is where we are. If it was a smooth pipe, we'd end up going across, here. And the friction factor would be 0.1, 0.11, something like that. That's still on the board. And if it was a rough pipe of some roughness, so in other words, if it was, what would a reasonable roughness be? So the pipe diameter is 1 centimeter. So if it were 1/1000th centimeters, then epsilon over d would be equal to 1/1000 over 1 centimeter. 1 centimeter is 10 to the minus 2 meters. So this would just be equal to 10 to the minus 3, 0.001, right? And so if that were the case, then 0.001 is this one. No, this one. Too many zeros. That would be this. And so this intersection here would be almost on the horizontal part, and it would be a friction factor of whatever this would be, which is 0.02. And so in that particular case, for this roughness pipe, the head loss would be equal to friction factor, length over diameter, v squared over 2g. And again, we know all these parameters. I probably won't embarrass myself by trying to calculate what it is, but this is, what was it, 0.02? Yeah, 0.02. Length is equal to 1 meter. Diameter is equal to 10 to the minus 2 meters. Gravity is 10 meters a second squared, or 9.81. And the velocity we defined as being equal to 100 meters a second. And so that's a simple exposition of a type 1 problem. Normally we'd know the velocity. We had to calculate the velocity to go into these two regimes because we're just working with a synthetic example. But the behavior that we get is just using this nomograph, figuring out what the velocity it is that either is sub 2000 or super 2000, defines exactly where it fits on this curve, and then you use that nomograph to be able to calculate what that frictional loss is. If you have a system which is not a simple one like this, but comprises a whole bunch of different components like this, then you're aided, I guess, by the fact that in this umbilical through the guy and then squirting down on the water, because of continuity, if the cross-sectional areas at every point in that pipe are roughly the same, then you could write this expression that the elevation difference here and the pump, which is what you want to solve for, then merely this sum of the losses is going to be k loss 1 plus k loss 2 plus k loss 3, I guess till 5. And also the head losses in the pipe as friction factor, length over diameter of 1 to 2, 1 to 2, and 1 to 2, etc. 2 to 3, and length over diameter, etc. But you could bracket those terms and, oops, run out of space, and you could multiply them by a common v squared over 2g. So if, for example, the cross-sections of the fittings and the pipe were the same all the way through, then you can take a single value of velocity out, because v1 a1 equals v2 a2, etc. And so you ease it, and all you need to know is what these loss coefficients are. Easy for these because these are just numbers. Bit more difficult for these because it matters what regime you're in, whether you're laminar or turbulent, but that's the calculation you need to do. So that's probably it for today. So I guess a bit more, as I said, this class gets to be a bit more like a recipe when you get closer to the end. We've done all the hard stuff. We know why these relationships are the way they are. And now what we're doing is really using a recipe to be able to figure out what the magnitudes of these individual behaviors are, with a bit of knowledge about what the characteristics are that make them the way they are. And the reason that these are constants is because they represent behavior on the far right of the Moody curve, where the only controls on the friction factor are the geometry of the fitting itself. How it goes around a bend, what the roughness is, and what the roughness of the pipe is. It doesn't care about what the Reynolds number is. And in the regime where friction factor is a function of Reynolds number, the laminar regime, it depends on the Reynolds number itself because it's driven by viscosity.